everyone, Chinnaiah Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equations. So let's get going. Problem: solve d cube minus d into y equals to e power x into x. So firstly, let's find the order and degree of the given differential equation. Identify the highest derivative here. D cube is the highest derivative, so 3 will be our order. And highest power of the highest derivative is a degree is 1. Or just write the given differential equation as d cube y minus dy equals to e power x into x. We know that d is a differential operator. Then d square will be, and d cube will be, right? Now, let's write the given differential equation as d cube y by dx cube minus dy by dx equals to e power x into x. Here, d cube y by dx cube is the highest derivative, so our order will be 3. And highest power of the highest derivative is a degree is 1. Now coming to the problem. Given differential equation, d cube minus d into y equals to e power x into x, which is an operator form. F of d into y equals to q, where f of d equals to d cube minus d and q equals to e power x into x. Now we need to find the general solution to the given equation, which is given by y equals to yc plus yp. Here yc is a complementary function, yp is a particular integral. We'll find yc using the roots of the auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by putting r equals to 0, we'll get f of d into y equals to 0, which is a homogeneous equation of non-homogeneous equation. So we'll find yp using 1 by f of d into q. So firstly, let's find roots of the auxiliary equation to write yc, and later we'll go for yp. The auxiliary equation of f of d into y equals to q, auxiliary equation of homogeneous equation is f of m equals to 0, where f of m equals to, we have f of d cube minus d, right? Let's replace differential operator by m, so that we'll get f of m equals to m cube minus m. Now our auxiliary equation becomes m cube minus m equals to 0. Now take m common from these two terms, we'll get m times m square minus 1 equals to 0. Let's write this 1 as 1 square. This becomes series of m square minus 1 square, which is of a square minus b square form. So we can write m square minus 1 square as m plus 1 into m minus 1. Right? Now equate each factor to 0. Already m equals to 0 is 1 root, and from m plus 1 equals to 0, we'll get m equals to minus 1, and from m minus 1 equals to 0, we'll get m equals to 1, right? Then m equals to 0, minus 1 and 1 are the roots of our auxiliary equation. Therefore, m equals to 0, minus 1, 1 are the roots of our auxiliary equation f of m equals to 0, which are real and distinct. Right? We know that when three roots, say m1, m2, m3 are real and distinct, then yc will be one constant into e power 1 root into x plus another constant into e power another root into x plus another constant into e power another root into x. Now let's write the complementary function. Yc becomes c1 into e power 1 root, say 0 into x plus c2 into e power minus 1 into x plus c3 into e power 1 into x, right? Then yc becomes c1 into e power 0 into x is e power 0 plus c2 e power minus 1 into x is minus x plus c3 e power 1 into x is x. Then yc will be, we know that e power 0 is 1, so we'll get c1 into 1 is c1 plus c2 e power minus x plus c3 e power x. So these are required complementary function. Now let's find particular integral. We'll find particular integral using 1 by f of d into q. We have f of d and q, where f of d is d cube minus d and q is e power x into x, right? Now, this is of 1 by f of d into e power ax into b form, right? Now compare this with, compare e power x with e power ax, and for a equals to 1, we need to find d plus a, which is equals to d plus 1. Later, we'll shift e power ax towards left by replacing d with d bar, d plus a, and later we'll operate b with 1 by f of d plus a, right? Now let's shift e power x towards left, we'll get 1 by f of d plus 1, right? We need to replace d with d plus 1 into x, right? This is equals to e power x into 1 by expand d plus 1 whole cube. We know that a plus b whole cube equals to a cube plus b cube plus 3ab into a plus b. Let's expand d plus 1 whole cube, which is equals to d cube plus 1 plus 3 into d into 1 into d plus 1, which is equals to d cube plus 1 plus 3d into d is 3d square plus 3, right? We'll get d cube plus 3d square plus 3d plus 1 minus into d minus d minus into plus minus 1 into x. So here plus 1 minus 1 gets cancelled. Then yp becomes e power x into 1 by d cube plus 3d square plus 3d into x. You notice we are having d in all three terms of denominator. So let's take it common. Let's take 1d common from all the terms of denominator. We'll get d times d square plus 3d plus 3 into x. Now let's split the fraction as 1 by d into 1 by d square plus 3d plus 3, right, into x. See, here we are having 3d minus d. 3d minus d is 2d, sorry. Here we will get 2d, right? Fine. Now, this is of some function of 1 by some function of d into x power k form, right? Now, we'll take, or we know the form 1 by f of d to x power k, right? So this is of 1 by f of d into x power k form. But here we have f of d equals to d cube minus d, but we are operating x for 1 by some function of d, say g of d. Okay, fine. Now take the lowest degree term common from all the three terms. Then we'll get, see, in the first two terms we don't have any 2. So what we'll do is, we'll just multiply and divide 2 to these two terms. Okay, so that in the next term it is easy to take 2 common. This becomes e power x into 1 by d into 1 by, now take 2 common from the two terms, we'll get 2 times d square plus 3d by this 2 plus 1 into x. See, 2 into d square plus 3d by 2 is 2 by 2 into d square plus 3d plus 2 into 1 is 2, right? Fine. This is equals to e power x into 1 by d into, we can split this fraction as 1 by 2 into 1 by d square plus 3d by 2 plus 1 into x is equals to e power x into 1 by d into 1 by 2 into, we can write the denominator as 1 by 1 plus, sorry, we can write this fraction as 1 by 1 plus d square plus 3d by 2 into x. Now this fraction is of 1 by 1 plus x form, right? We can write it as 1 plus x whole inverse, and later we can use binomial series expansion. This becomes e power x into 1 by d. E power x into 1 by 2 can be written as e power x into e power x by 2 into 1 by d into, we can write this fraction as 1 plus d square plus 3d by 2 whole inverse into x. Now before expanding this, let's find the derivatives of x. Derivative of x is 1. D square of x is derivative of x. We know that derivative of x value is 1. And here we need to find derivative of a constant which is 0. Likewise, d cube of x will be 0 and so on. You'll get higher derivatives of x 0. Right? In general, we can write it as d power k of x equals to 0 for k equals to 2, 3 and so on. So we can neglect higher derivatives of x from d square, d cube and so on, right? Now keeping this in mind, we'll expand this using binomial series expansion. Let's expand 1 plus d square plus 3d by 2 whole inverse into, okay, whole inverse using 1 plus x whole inverse and expansion 1 minus x plus x square minus x cube plus so on. We know that higher derivatives d square of x, d cube of x so on becomes 0, right? Fine. Now let's expand this. We'll get 1 minus, just compare 1 plus this term with 1 plus x. So for x equals to d square plus 3d by 2, we'll get 1 plus d square plus 3d by 2 plus d square plus 3d by 2 whole square minus d square plus 3d by 2 whole cube plus so on, right? This is equals to 1 minus d square plus 3d by 2 plus expand, we can expand later, d square minus 3d whole square by 2 square minus d square plus 3d whole cube by 2 cube plus so on, right? Let's expand d square plus 3d whole square is equals to d square whole square plus 3d whole square plus 2 into d square into 3d, which is equals to d square whole square is a power m whole power n is a power m into n to 2 is a 4 plus 3 square is 9 into d square plus 2 3 is a 6 into d square into d power 1 is d cube, right? So here, what are the higher derivatives? D power 4, d square, d cube, all are higher derivatives, right? If this term has higher derivatives, then definitely this will have higher derivatives, right? So we can neglect all the terms from here, right? Because higher derivatives of x from d square, d cube and so on become 0. So we are going to neglect terms from here, okay? Now, coming to YP, let's expand this. YP becomes e power x by 2 into 1 by d into 1 minus d square plus 3d by 2 plus d square plus 3d by 2 whole square minus d square plus 3d by 2 whole cube plus so on into x, right? The same expansion we have written here and use this formula. Fine. This becomes e power x by 2 into 1 by d into 1 minus d square plus 3d by 2 plus d square plus 3d whole square by 2 square minus d square plus 3d whole cube by 2 cube plus so on into x, right? This term. Since d power k of x equals to 0 for k equals to 2, 3 and so on, so neglect higher derivatives from d cube, sorry, it involves d square also, right? D square, d cube and so on, okay? So we are going to neglect from here directly and I'll write just first two terms, that's enough. Because already we have mentioned that we are going to neglect higher derivatives, so we can neglect from here directly. Instead of neglecting d square first, we'll just neglect all the terms from here and later we'll neglect d square from this term. E power x by 2 into 1 by d into 1 minus d square plus 3d by 2 into x is equals to e power x by 2 into 1 by d into 1 minus 1 by 2 into d square, right? Minus into plus minus 3d by 2 will be 3 by 2 into d into x. Now we can neglect this term because it has d square, higher derivative, right? Either you can directly neglect this term from here, or later you can apply the value 0 for d square of x. Okay, so I'm going to neglect. I'll get 1 minus 3 by 2 into d into x. This is equals to e power x by 2 into 1 by d into 1 into x is x minus 3 by 2 into derivative of x is equals to e power x by 2 into 1 by d into x minus 3 by 2 into derivative of x is 1. This becomes e power x by 2 into 1 by d into x minus 3 by 2 into 1 is 3 by 2. We know that 1 by d is an integral operator. So let's integrate the two terms under brackets. This becomes e power x by 2 into integral x dx minus integral 3 by 2 dx. Here 3 by 2 is constant, so take it outside the integral. We'll get integral x dx minus 3 by 2 into integral dx. This becomes e power x by 2 into x square by 2 minus 3 by 2 into integral dx is x. We can write this as x square minus 3x by 2, right? Is equals to e power x by 2 into, again we can split this as 1 by 2 into x square minus 3x. This becomes e power x into 1 is e power x by 2 2s are 4 into x square minus 3x, which is our yp. Therefore yp equals to e power x by 4 into x square minus 3x. We got yc and yp, so let's write the general solution. Therefore, the general solution is given by y equals to yc plus yp. Then y equals to yc, we have c1 plus c2 into e power minus x plus c3 e power x plus yp. E power x by 4 into x square minus 3x. This completes the problem. So we have seen a problem from higher order linear differential equations in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.